Today we're going to do section 9.4. So first, let's look at the book. This is just the old page that we already scanned earlier with a little bit of new stuff, so that's it. Next, page 296 and 297. Let's see, first the whole page. Back a little bit there. That looks okay, I guess. And then a bit closer on top. Okay, a bit closer on the bottom. Okay. Next, page 298 and 299. First, the entire page. Let's see, maybe like this. And then a bit closer on top. And a bit closer on the bottom. All right, that's good enough. All right, so today let's start at section 9.4, limit test, which is on page 296. There's a little bit on 295, some quick introduction, and also on the following page. And that please read that yourself, okay? And we will proceed with subsection 4.1 on theorem 9, which states that the limit, if the limit of k to the power p times u of k. So sum of u of k is your sequence. Your series. However, we're going to slap the k to the power p on top as a test. So if you can find some k to the power p some integer bigger than 1, if you can slap that onto uk, and then the limit, the individual terms limit at that point equals to a fixed number, the fixed number cannot be infinity. Okay, it doesn't say infinity, it cannot be infinity. But anyway, if kp you can get it to equal to some fixed number, then you have proven that the series converges absolutely. All right, so to prove that, then we see that the first step, being that the limit goes to a, that means the absolute value of everything, of course, also go to absolute value of a, then we will be able to come up with manipulations, okay? That means that the sequence then going to be less than a plus 1 as long as the k is big enough. And then rearranging this, we get uk is less than sum of the number times k to the power minus p. Now, what is k to the power minus p? We've seen that. That is test series T2, which is on page 286. So let's look at that again in the previous page that we have covered. Now, the test series T2 is 1 over k to the power p is presented to be, for p bigger than 1, it converges. Everything else diverges, period. Okay, so that is so that's why this theorem also says the requirement is that p bigger than 1. Why? Because once p is bigger than 1, we're down here, then it satisfies the T2 test series T2 test. Okay, so then this thing then is less than T2, well, times the absolute value plus a bit, but that's just a constant, and therefore it is convergent. So having said that, then let's look at example A, which is rather straightforward, I think. So please do that yourself. Example B, same thing, also quite straightforward. So please also do that yourself, as I have done it. Okay, this is for your reference. And anyway, so let's move on to the next part, theorem 10. Yes, subsection 4. Now we just did the test for convergence. Now we're going to do the test for divergence, the both limit test. Now for the test of divergence, it says that if the limit, you slap 1k on there, okay? If k times uk is equal to some kind of a number, and that number can be infinity, it's okay. So, but if you can prove that A equals to a number, including infinity, then the sequence diverges. Sorry, the series diverges. Now, if it equals 0, if A equals 0, then the test doesn't work. So you can forget it. But as long as you can get it to be equal to something that is not 0, then we're good to go. And so let's look on the next page for the proof. Case 1, first let's consider when A is positive, which is a positive number or positive infinity, doesn't matter. Then if that is true, then of course as k gets bigger, then each term is, then at the end of the term, then k times uk is going to be bigger than a over 2, being that, don't forget, the ku is approaching a, right? So then when the index is big enough, it should get at least up to a over 2, and a is positive, so it should get up there. And if this is the case, then this is for all big enough k. So then as a result, this thing then compares to the harmonic series in this way. Let me show you here. So then because of that, then since we have k times uk is bigger than a over 2, manipulate the algebra a little bit, then uk will, on the side, uk will be bigger than a over 2k. That is the sum of uk. It compares to the harmonic series, right? So the sum of uk right here is bigger than the sum of a over 2 divided by k, which as the harmonic series is bigger than something that diverges. Therefore, it diverges. So that is the standard proof for the case that a is bigger than 0. Now, what if a is less than 0? Then we just slap a negative sign on every single thing. Okay, and if it's less than 0, slapping a negative sign on there will make the whole thing bigger than 0. Let me think about that. Well, if the limit is negative, that means eventually this sequence, if we slap the negative sign on there, then eventually the limit will be positive. Then we can just apply case 1 instead. And if the negative terms all converge, then the positive one will also converge. Anyway, so case 2 is just slapping the negative sign there, which made it positive, which fits case 1, and then we can use the criterion of case 1 to handle this. So that's that. And so that's the cases when a is bigger than 0 and a is less than 0. What happens when a is equals to 0? Then we have two examples when to show that the test doesn't say anything, okay? Because the first sequence we can think of is this one, 1 over k squared. The series 1 over k squared, obviously convergent. But this one is obviously divergent. Well, if you don't remember why this is divergent, just look at T3 on the test series 3 on page 290, which states anything that looks like that. Okay, T3 on page 290 is right here. See? Is this thing says that this is what we did earlier, and then this says that if p is bigger than 1, okay, if p is bigger than 1, then well, never mind. Well, if p is equal to 1, this series diverges. Okay, that's what it says right here, and therefore this series diverges, and as it says right here, it's based on that. So those are the cases, and both situations can happen if a equals to 0. The next, let's look at example C. Example C, I think is, so we just try using the theorem 10, the limit test for divergence, and it works out. I think example C works out pretty nicely. You just have to write stuff out, and then everything becomes quite obvious. Okay, and so please do that yourself. And then next, example D. Now, example D, we have an alpha and a beta. Okay, so which means you have many cases. I don't know, 5 or 6 different cases of what happens depending on whether alpha is positive or beta is negative or something like that. So I did some of that I didn't do all of it because, frankly, I ran out of steam. Okay, I was bored with it. So I did some. So please do some of these yourself. Do as many as you can. If you get until you get tired of it, then let's just move on. All right, I will just take the author's word for it that this all the stuff works out. Yeah. So now we have come to the end of this section. For homework, let me write it down first. So for homework on page 298, section 9.4, please do problems 1, 2, 4, 6, 8, 9, 10, 11, 12, and 14. And for problem 14, I have a hint here. Okay, you can also do it. Well, you try to figure out the hint, but it just is a bit tedious to me. Okay, let's just, I rather just look at the hint and call it that. The hint is this sentence right up here. Okay, the rest of it is the proof of the hint. So I have Google type out the proof to why this is true. Okay, this is generally true, and here's proof how to do it. But this equation right here, this and that thing, is what you might need for doing problem 14. Okay, so that's that. So please go do your homework. Okay, so now let's look at problem 1 on page 298. Well, actually, problems 1, 2, 3 are to redo some past problems, which I don't think any of them are particularly long, so it was okay to do them. Okay, and there's not much worth mentioning here. So there's 1, 2, and 4 here, I believe, and then problem 6 is a similar deal. Problem 8 is problem 8. By problem 8, I was getting confused by all the logs. Okay, it's like, what are we doing here? And but here's the trick that remember that the natural log of k squared uk end up being equal to natural log of 2 minus something. Okay, and that end up being infinity times minus infinity, which is negative infinity. So therefore the original function, so the trick is to take the natural log and show that it goes to negative infinity, which means the original thing goes to 0, and therefore it is convergent by theorem 9, and that's problem 8. Well, I hope it's correct anyway, because by now I didn't bother double checking anything, although of course problem 8 does have the answer at the back of the book. Okay, so next let's look at problem 9. Now, prove or disprove. If UK, the absolute value, is bigger than 1, then that means the series UK diverges. Well, that is true for the absolute if we slap the absolute value on UK. That is, if following if each UK, if we slap on the absolute value, okay, is bigger than 1, then of course we can move the k to the bottom, being that k is positive, means each UK is bigger than 1 over k, the harmonic series, and therefore the sum will diverge. However, the question is, what if you take the absolute value out? For example, what if UK equal to, say, this thing right here, okay, that I concocted, and in that case, then each UK, UK times k will be equal to 2, which is bigger than 1 as required. However, the sum, being that it's an alternating series, the alternating harmonic series, it will converge. Therefore, the statement is false because it's only true some of the time. So that's problem 9. Next, let's look at problem 10. Problem 10 is a cute little problem that says that has a function f in it. We haven't seen that many function f in the series, but now it has a function f, and the series is defined by the function f. Okay, so our series is the value is adding up the value of f at 1, 2, 3 unto infinity, and now we're supposed to prove or disprove. Suppose f is continuous. That matters a lot. Okay, so and x times f of x is bigger than 1, all right? And then x is bigger than or equal to 1, so we don't have to worry about negative values or even 0. So then that would mean the sum diverges. Now to prove that, we have, let's see. So I have it written down here. To prove that f is what this means is that if absolute value of x f of x bigger than 1, that would mean k f k is either bigger than 1 or k f k is less than minus 1, right? Now, if that is the case, then we have now I repeat that sentiment here. However, now there's one important point, that is f is continuous, so f cannot be 0. That is, f has to stay either on the positive side or on the negative side. It cannot cross the x-axis. So if f, let's say f start out being positive, then it'll stay positive forever, okay? And because of this requirement right here, x f x, it has to be bigger than 1, and f is continuous. So in other words, if it's continuous, it cannot jump over it has to cross the x-axis to become negative, or to change, in other words, to change sign, it has to cross the x-axis. That means it has to be 0 at some point, and it cannot be 0 because x f x is always bigger than 1 when x is positive. So f of x is locked out. Okay, it's not allowed to cross the x-axis. So the entire sequence consists of either all positive values or all negative values. Now, if that is the case, then of course, then we can argue that the sum will be either bigger than the harmonic series or less than the negative harmonic series. Either one, that means they will diverge. Therefore, the statement is true. So next, let's look at problem 11. Prove that if this equals to A and P is bigger than 1, that means the sequence converges. Absolutely. Now this theorem reminds us, this problem reminds us of, it definitely reminds us of the limit divergence test, that is theorem 10. So let's look at that. Right, that is theorem 10. The only difference is there's a log stuck in there, but otherwise it reads about the same. So we're going to simulate the proof of theorem 10 in trying to get problem 11 to work. Okay, so let's do that. And also, in being similar, then we also simulating another test series, which is test series T3, which is on page 290. We just looked at it. Let's look at it again. Let's see, test T3 on 290 says this. If this is for this series that looks very much like what we have in the problem, then this thing converges for p bigger than 1, okay? And diverges otherwise, I guess. Yeah, p equal to 1 to 0, then it diverges. And therefore, we are going to do that. But first, let me see what the problem wants. Maybe I should figure out what it wants first. So problem 11 says, again, that the series converges absolutely, right. So let me, having read that, then let's see what I have. Now, the limit is equal to A for p equals to, we only care about p is bigger than 1, right? Okay. So if the limit equals to A, then simulating, what is it theorem 9 or theorem 10 that we're simulating? Maybe I told you the wrong thing. Maybe we're simulating theorem 9, okay? And yeah, we're actually simulating theorem 9, not theorem 10, because we're doing convergence. Theorem 10 is divergence. But anyway, so this is what we're simulating, which is fine. And let's simulate it. Okay, so copying theorem 9, we have that the limit is equal to A, which means when they're big enough, it should be less than the value of A plus 1, and which means the terms themselves will be less than this, okay? And then and this term is known to be convergent for p bigger than 1, which is on page, that is T3, is convergent for p bigger than 1, and you can look at that again on page 290 to be absolutely sure. Anyways, convergent, and that's good enough for me. So next. Okay, next let's look at problem 12, which says that this limit of this thing, if this thing is equal to a, which is not 0, so then the series diverges. That definitely reminds you of theorem 10, so that's what we're going to simulate. Now, knowing that, I have it written down here. We have this thing is because the limit is equal to a, let's say a is positive for now, okay? Just like the proof of theorem 10. So if it's approaching a, then sooner or later it's going to be bigger than half of a being positive. Then which we rewrite terms, then UK is bigger than this thing right here, and this thing diverges by the test T3. Let's look at it again. Test T3 says on page 290, which says that here's test T3, which says that it diverges for p equal to 1. Okay, right down here. So that's how we. So then, therefore, our series diverges. If I can find it, where did it go? Okay, right here. Now, so the series diverges if A is positive. If A is negative, we do exactly as in the proof of theorem 10. Just slap the negative sign in there, okay? And still diverges. Just maybe go to the other infinity is all. So that is problem 12. Next, let's consider problem 14. Problem 14 is the one that I gave you the hint. Let's look at the hint again. That made things much more pleasant. Okay, otherwise you're just stuck without a hint and just it's not that much fun. Anyway, the hint is this thing. Now, how do you prove this thing? To prove this thing, we do this the calculus trick where you show that where you define a function f as the difference of these two things and show that the function is 0 as 0, and for bigger than 0, the derivative is bigger than 0. Okay, so then which means it's strictly increasing. It's bigger than 0 as 0, so then it goes up from there. Therefore, f of x is bigger than 0 for all of them, and therefore this thing stands. The other part is the same way, and yeah, it's just it's the old calculus trick of proving that the derivative is strictly increasing if it is, which it is at this point. So if you want to, you can work out the details yourself. Okay, here are all the details that Google showed me. But anyway, so now that we know that this hint is correct, then the rest of it is just a matter of comparison. Okay, now that we have the hint, then we can plug things in. Like, for example, the a, we can rewrite a, okay? A is raised to the power log k, which is another way of saying that is the denominator is also equal to log k raised to the power log a if you beat around the logs a little bit. Then it all comes out right here. So once you know that, then we have the log k to the power log a, and which you can rewrite, which this is going to be less than this equation, okay? And that how do we know this? This is by this thing. Our hint is the hint can be rewritten as this when you substitute x for 1 over k. See, so once x becomes 1 over k, then this situation happens, and the whole point of that is to prove that log of 1 plus 1 over k is less than 1 over k. That is using this part of the equation right here. So once we got to this point, that looks identical to test T3 on page 290, which converges if p is bigger than 1, and therefore this thing converges. Okay, if p, which in this case is log of a, is bigger than 1, which comes out to be if the a absolute value of a is bigger than e. Now on the other hand, on the other side of the equation, this value is bigger than 1 over k plus 1, plugging that in, and similarly, then we can figure out that this thing is bigger than a series that does where p equal if a is smaller than or equal to e, then log of a is smaller than or equal to 1. If p is smaller than equal to 1, then it diverges, and that is that. Now when I was googling to see how how they want this done. The Google at first recommended that I use the Taylor expansion. Okay, just that is, just expand this thing. Okay, once you expanded it, then you know that this is the similar log 1 plus k is similar to 1 over k, which is true, but we don't have a theorem that proves it. That is, the only theorem we have of proving using Taylor expansion to calculate order of infinity, which is theorem 5 on page 272, right? So let's look at that. The reason we can't use that is because the theorem we have is specifically states that we are comparing the n plus 1 derivative of things. Okay, and right now the Google wants me to take the compare Taylor series of one of them, but not the other. See, before when we used theorem 5, we did the Taylor series of both, expanded both Taylor series, and then because that is what the theorem says to do. Now, without that, then we don't have enough theorem to use that trick, which is why I recommend that you don't use Taylor series. If you're only going to expand one of them, I mean, you're supposed to expand both of them. Of course, expanding this thing is I'm not sure how to expand this thing. Maybe there's a way, but it's not exactly a neat form. So basically, well, the Google did not bother expanding the denominator. It just says, well, the numerator is almost 1 over k, so we just plug it in, or it works out. But that's just not good enough. Okay. To do this, which is why this one, however, is absolute solid. This is totally true. There's no getting out of it, and therefore this is a better solution instead of doing hand waving. Hey, look, that is good enough. Let's just get going. And no, it's better to follow our theorems completely instead of pushing it. And so that is the end of this section.